The Sun, the star which keeps all the planets of the solar system in their orbits and the source of all our heat and light. It's a gigantic ball of gas, unimaginably hot. Storms rage constantly on its surface, explosions of superhot gas called solar flares, reaching millions of kilometers into space. Less visible parts of the Sun's atmosphere interact with our atmosphere, causing electrical storms. Naturally, scientists keep the closest possible watch on solar happenings. So NASA, the American Space Agency, built the Solar Maximum satellite, which carried several experiments, each designed to look at a different feature of the Sun. The satellite was launched on Valentine's Day, 1980, a year of solar activity. And the first results were spectacular. But then, to the dismay of world scientists, the signals suddenly stopped. Failure of several key components meant that the multi-million-dollar satellite could no longer be made to point at the Sun or to carry out all of the experiments. Still, all was not lost. This satellite had been designed so that it could be repaired in space. And that was one of the jobs NASA had always planned for its space shuttle. The Solar Maximum repair mission began to take shape. Of scientists and engineers were called in to plan the mission, and an 18-month training period began for the shuttle crew. A huge water tank contained a full-sized mock-up of the shuttle. It gave the crew an idea of what it would be like in space. The astronauts were fitted with weights to balance the water's upthrust on every part of their bodies, so they felt weightless, as they would in orbit. Obviously, no space flight, especially one this complicated, would be possible without a vast amount of planning and organization. In another simulator, with outside views provided by computer graphics, the astronauts practiced controlling the equipment in the shuttle. Computers were everywhere, both in the shuttle and on the ground. These are thousands of times more powerful than the best micros. The maths of spaceflight are very complicated indeed. And yet some of the most important ideas were put forward over 250 years ago by Sir Isaac Newton. Newton would have seen firework rockets, but could never have imagined anything like the shuttle on the launch pad.
7, 6, 5, 3, 2, 1, 0.
But he could have given a good scientific commentary of the liftoff.
5, 6, 7, 8, 9.
He would have explained the way the rocket works by describing what happens when a gun fires. The gun doesn't stay still. The explosion, which pushes the shell forwards, also pushes the gun backwards. The gun recoils. The shell moves one way, the gun the other. The same thing would happen without a shell as long as there was an explosion. As the gas comes out, the gun would recoil. Sir Isaac Newton would probably think of the rocket as being like the gun firing constantly downwards and recoiling constantly upwards. At launch, the motors have first to give enough thrust, enough force, to balance the weight of the shuttle. Then only a small increase in thrust would be needed to overcome its inertia and get it moving. At first, the shuttle moves slowly, but then it picks up speed. The motor continues to push the shuttle faster and faster. It accelerates from a standstill to over 30,000 kilometers per hour in only 8 minutes. As it uses up fuel, the mass decreases, and so the acceleration increases. The shuttle doesn't go straight up, it follows a gently curving path. After 2 minutes, the boosters are almost used up and will fall away. Soon the shuttle will have to rely solely on its own engines, but its mass has been greatly reduced by burning fuel, so less thrust is needed to keep it accelerating. Once at the top of its path, the engines are turned off. But it doesn't fall back again. And keeping the engines firing isn't the answer. The shuttle would shoot off into space. When the engine's turned off, the shuttle does begin to fall, but the surface of the Earth is curved. As the shuttle falls towards the surface, falls away from it. That's why being in orbit is called being in free fall. The shuttle is moving very fast, so it's tending to shoot off in a straight line. It doesn't because the Earth's pull, gravity, keeps pulling it round. Being in orbit brought new experiences for the crew. In free fall, everything behaves as if gravity had been switched off, as if everything was weightless.
You gotta go. Again?
And it's easy to launch satellites from a free-falling vehicle.
Have a good one, mate.
The manipulator arm can be used light out of the cargo bay and hold it over the side.
Potato to potato. And I did get the chattering.
They carefully let go, making sure that the satellite is never speeded up nor slowed down. The satellite will also be in free fall, moving as fast as the shuttle and in the same orbit. It'll keep moving like this even if the shuttle moves away. The damaged solar maximum satellite higher orbit. To get into that higher orbit, a small engine in the shuttle was fired, giving the shuttle a forward push and speeding it up. The result was that it spiraled outwards into a higher orbit. Then came one of the most delicate parts of the mission. The pilot had to maneuver the shuttle alongside the stricken satellite. Small adjustments to the height of the orbit and the position in the orbit can be made using small thrusters. To the astronauts, free falling with the ship, it seems that when a thruster is fired, the shuttle moves off in the opposite direction and continues moving. until an opposite thruster is fired. To move back, that thruster has to be fired again. And the original thruster seems to bring the shuttle to a halt. The same technique is used for movement in other directions.
Yeah, I sure do, thanks.
Start. Stop. Go back. Stop. The shuttle and the satellite are hurtling round in orbit. By careful use of the thrusters, the pilot manoeuvred the shuttle to within 100 meters of the satellite.
The real moon approach. Okay, thanks. Check your alternate cot modes as required.
And now, suit up. And for another member of the crew, it was time to put training into practice.
They are retracted. Okay, rod release. Ready? In the green. 30 degrees. Helmet lights on. Helmet lights are on. And your front.
To get to the satellite and to make small changes to it, the astronaut had the MMU, the Manned Maneuvering Unit. "300 meters can be a long way in space. The MMU is maneuvered by very tiny thrusters, but in the same way as the shuttle.
Okay, thank you. Send out there at about 140 feet at this time. Sure.
He had no sensation of hurtling round in orbit. He felt as if he was floating weightless and using the MMU to move around. As the MMU is small, the thrusters need only be small.
You're looking good there, sir.
Still, the astronaut had to use the thrusters gently. Too much, or in the wrong direction, and he would have pushed himself dangerously off course. Everything had to be working perfectly before setting off to the satellite.
Like you might need to come up.
The problem was that the satellite was rotating. The astronaut had to move over and stop it rotating.
I got it setting high on the orbiter anyhow.
The idea was for him to match the spin of the satellite, then clamp on and use the thrusters in the opposite direction and so stop the satellite spinning. At least that was the theory. In fact, because his mass was low and the much more massive satellite was turning quite quickly, he was knocked away. In desperation, he tried applying the force from further out, on the end of the solar panels, hoping to get a larger turning effect. He managed to slow the spin, but couldn't stop it. For the astronaut, there was nothing more to be done other than return to the shuttle. But luckily, that wasn't the end of the story. The mission controllers back on Earth could now try the satellite's own thrusters. Thanks to the work of the astronauts, they were able finally to stop the spin. During the night, the crew used the manipulator arm to grab the satellite and to bring it on board.
Head backwards towards us, rotate around. To your left, continue left. I mean, which way's the satellite? Excuse me? What kind of rates are on the satellite? They're fairly high, but come back to us. Rotate around to your left.
The repair work could begin. The best working position for the crew turned out to be fastened on the end of the arm. Repairing delicate electronic equipment in space is no easy job. Thick space suits and gloves don't exactly help. On Earth, using a screwdriver or drill is no problem, but in free fall, if you use a drill on something much more massive than you are, then all that happens is that you... To stop that happening, the astronauts' feet were firmly fixed to the platform on the end of the arm.
Get my pitch squared away, I'll go in and down.
After many hours of hard, dedicated work, the replacements were fitted and repairs complete. And on the end of the arm was needed to check everything. Then pick up the satellite and put it over the side again. And let go. The scientists back on Earth put the satellite through its paces. Everything worked perfectly. For the crew, it was time to think about returning to Earth. The shuttle was turned around and the rocket fired. A force in that direction slowed the shuttle down. The shuttle began to fall earthwards. Cabin checks were completed. Doors closed. Had the repairs not been successful, the satellite would have been brought back to Earth in the cargo bay. Soon, the shuttle met the upper level of the atmosphere. Friction between the fast-moving shuttle and the air heated up the outer skin. That friction also slowed the shuttle down even more.
6,600 feet.
When there was enough air, the shuttle acted like a plane, or, as there's no engine, like a giant heavy glider. The force of the air pushing on the wings or the tail meant that the pilot could control the shuttle, maneuver it towards the landing strip, and the end of what turned out to be a most successful mission.